this video, we're going to talk about van der Waals equation. We're going to talk about the parameters in the equation, but first we're going to look at some PV diagrams and see what information the PV diagrams can tell us. We're going to then use this information to see how we can go about deriving the parameters in van der Waals equation. Then we're going to take a look at the compressibility factor of a non-ideal gas.
Let's take a moment to define what a PV diagram is. A PV diagram is a diagram that shows us the relation between pressure, temperature, and volume of a pure substance. Before we move any further, we must define what we mean when we say volume. So when we refer to volume, we mean the specific volume. The specific volume is the volume for a certain quantity. This means volume per a certain mass or volume per a certain number of moles. So the units for this would be meters cubed for volume per kilograms or meters cubed per moles. So now that we have defined that, let's take a look at our diagram on the left here. We can see that on the x-axis there is temperature and on the y there is pressure. We can also see that there are three regions. There is the vapor region, the liquid region, and the solid region. And then we also see three intersecting lines that intersect the regions. So what that means is that on any point of the line, it is an equilibrium of the two states that it is intersecting. So for example, on, let's say, this curve here, this line here, it is intersecting the vapor and the liquid region, which means at any point on this line, it is in equilibrium. Now, as we move up this curve, we see that temperature is increasing, and we see that it moves all the way up until right here, and at that point the line doesn't continue, but rather it stops and we enter this fluid region. So the point at which the line stops is called the critical point. Let's take a moment to define what the critical point is. The critical point is when the liquid and vapor properties of the substance becomes indistinguishable. One of those properties that we know is the refractive index, or the speed of light. This property becomes indistinguishable. So what that means is if we were to have a cup of water, a lot of times when you look at a cup of water from the side, you will see this thing called a meniscus. The meniscus is the line that kind of shows you where the water is, right? So you can see that up here there is air and down here there is water. So when we hit this critical point, what happens is that meniscus disappears and you can't really see where the water starts or ends, or the liquid water starts or ends, or where the vapor water starts or ends. It kind of just all looks the same. And that is what we call the fluid region. So in the fluid region, you can't really tell where the liquid is and where the vapor is. Its properties are indistinguishable. They are the exact same. So if we move on over here to this PV diagram on the right, we now see that volume is on the x-axis while pressure remains on the y-axis. But then we have these red lines here, and what these red lines are they're called isotherms. So let's take a moment to define what an isotherm is. An isotherm is a line that shows constant temperature. So let's say we take a look over here. We can look at these blue points on the same isotherm line, and we can say that they have the same temperature. Likewise, we can look at these purple points on this isotherm line and say that they have the same temperature. But the blue points and the purple points do not have the same temperature as they are on different isotherms. So that's what an isotherm is. And if we take a look at this pressure versus volume with isotherms, what we can see is a few things. We see this point right here. This point is similar to this point, and it is just the critical point. The point in which the liquid and water vapor become indistinguishable. So then we have this kind of bell-shaped curve that intersects with an isotherm right here. And underneath it, I don't know if you noticed, but it says, it's kind of blurry, but it says the mixed liquid vapor region. This is what is called the fluid region on this graph over here. And so what that basically means is that what is under this curve is indistinguishable between liquid and vapor. This is the fluid region. And so if we take a look here, we see that there is a point. The point is at this specific volume. Let's take a note that it's specific volume. It is at this pressure and on this isotherm. So what that means is that this temperature right here is the critical temperature. It's the temperature that the substance, in this case we're going to reference water, needs to be in order for it to be at its critical point. And then down here is the critical specific volume. That means at that point, this is the volume that the substance, in our case water, needs to be at the specific volume in order for it to reach its critical point. And then likewise, this is the critical pressure. Similar to temperature and volume, it's the pressure that is needed for the substance to reach its critical point. So when the substance is at its critical temperature, critical specific volume, and critical pressure, it will be at this critical point. Now if we move on down here, this looks like a lot, but it's more of just what we've been talking about. If we look at the diagram on the left, and we look at this diagram on the left, we can see that they are the same. It is the same temperature on the x, pressure on the y-axis, and if we take a look over here, we can see that it is the same as the graph on the right. It is volume on the x-axis and pressure on the y-axis. And so when we move on over here, we can see that they are now combined to produce a pressure, volume, temperature diagram. And so when we look, we can see that this critical point lines up to right here, and this critical point lines up right there. So this point right here is our critical point. And as we mentioned before, under this bell curve that's really just under this curve, is the fluid region, the point where the vapor and liquid are indistinguishable. And so on this graph, it is this surface here that is the fluid region. So now that we've taken a moment to talk about some defining terms as well as taking a look at the PV diagram, what those look like, let's take a pause from the diagrams and move on over to van der Waals equation. Now, van der Waals equation is an equation that relates pressure to the temperature to the volume. So van der Waals equation was an equation that was derived from the ideal gas law equation, which is P, pressure, times volume, equals moles times the gas constant R times T. So we are going to assume for our purposes that the specific volume in this case is the volume per 1 mole. So since this N is 1, we can remove it, and we will be left with pressure times volume equals the gas constant R times temperature. So van der Waals took this equation and wanted to write an equation where you could find the pressure at any temperature and volume. Now he had to add a few parameters. The first parameter that he added was pressure equals gas constant R times temperature divided by V minus B. So this B is the volume between the atoms of the gas. So if we take a look at a closed container, say we have this closed container here, there's going to be, on a very sized up level, like if you were able to zoom in super close to the molecules cannot sit on top of one another. They actually are spread out. But so what that means is that there is all this space between them. So what the parameter B accounts for is this space here. And it basically is the excluded volume. Now the second parameter that van der Waals said was this A over V squared. So the parameter A is the attractive force from the induced dipole and the spontaneous dipole reaction. So again, if we have a closed container and we have all these gas molecules inside, what happens is they get pulled towards one another, and as they are pulled towards one another, what's happening is they're being pulled away from the edges of the container, and as they're pulled away from the container, the pressure is going to decrease because it's not bouncing off of the edges of the container no longer, because they're being pulled inwards. So that's why it is a subtractive parameter. That means it is being subtracted from the actual total. So this is the van der Waals equation of state.
So now that we have looked at van der Waals
equation and the parameters A and B in van der Waals equation and what they represent, let's relate van der Waals equation to the PV diagrams and the critical points we were talking about earlier in the video. So when we look at van der Waals equation, we can see that it is an equation to find the pressure at any given temperature and any given volume. So it relates pressure to temperature and volume. Wait a minute. That's what a PV diagram does. It is relating pressure to temperature and volume. So if we take a look at this PV diagram over here, we can see that it is volume to pressure to the temperature, that is the isotherms. And if we take a look at this curve here that shows where the fluid region is, so the fluid region is underneath, we mentioned it earlier. I just got rid of it so it looks a little cleaner for you guys to see. We have this curve here that shows how the pressure behaves according to the volume at certain temperatures. And so when we look at the top here, which is where the critical point is, we can see that the slope of this curve is equal to 0. And then we can also see that as this curve goes up, it is concaving up and then concaving down. And so keeping the fact that it is a slope and the fact that it concaves up and concaves down, which is also called an inflection point, in mind, if we go down back here to the van der Waals equation, we know that when you have the slope of an equation, that can be calculated, or the slope of a curve, that can be calculated using the first derivative. So that would be dp over dv. But we stated that at the critical point, it is equal to 0. We also know that the inflection point is the second derivative, and that is also equal to 0. But for van der Waals equation, it is for any given temperature and any given volume. But on the PV diagram, it is just at the critical point that the first derivative and the second derivative of van der Waals equation is equal to 0. So we must state that. So we are going to state that the temperature is the critical temperature and the specific volume is the specific critical temperature, or critical specific volume. Now, we're going to do the same for the second derivative, so temperature equals the critical temperature, and then volume equals the critical specific volume. So now let's just take the first derivative and the second derivative of van der Waals equation and see what we get. So for the first derivative, we are going to get negative gas constant R times the temperature, the critical temperature, remember, divided by the critical specific volume minus B, that quantity squared, plus 2A over the critical specific volume cubed. Now if we take the second derivative, we are going to get negative, or positive, my apologies, positive 2 gas constant R times the critical temperature divided by the quantity of the critical specific volume minus B cubed minus 6A over the critical specific volume to the 4th power. So now what I'm going to do is I'm going to move this, and these are both equal to 0 as we stated up there. So I'm going to move this quantity over to this side and this quantity over to this side to get rid of those nasty negatives. And that's going to leave us with the gas constant R times the critical temperature divided by the quantity of the critical specific volume minus B squared, which equals 2A over the critical specific volume cubed. And then for the second derivative, that's going to leave us with 2 times the gas constant R times the critical temperature divided by the quantity of the critical specific volume minus B cubed, which is equal to 6A over the critical specific volume to the 4th power. Now, in order to put these two equations, the first derivative and the second derivative, together, what I'm going to do is I'm going to take this quantity on the left and multiply it by the reciprocal of this quantity. And then I'm going to take this quantity on the right and multiply it by this quantity. the reciprocal of that quantity. So that's going to leave me with gas constant R times critical temperature divided by the quantity of the critical specific temperature volume minus B squared multiplied by the critical specific volume minus B cubed over 2 times the gas constant R times the critical volume on the left side. And then on the right side, I am going to have 2A over the critical specific volume cubed multiplied by the critical specific volume to the 4th power over 6A. And so canceling some terms out, I am going to be left with just one quantity of the critical specific volume minus B on the left side, and then I'm going to cancel out the gas constant R and T, only being left with 2 in the denominator. So critical specific volume minus B over 2. And then on the left side, the A's will cancel, the critical specific volume on the bottom will be removed, and then I will only be left with 3 in the denominator, so that's going to give me the critical specific volume over 3. So now to solve this, I'm going to move 3 onto that side and 2 onto that side. So that's going to give me 3 times the critical specific volume minus 3B equals 2 times the critical specific volume. So moving things around, I'm going to have 3B equals 3 times the critical specific volume minus 2 times the critical specific volume. So that's going to leave me with 3B equals the critical specific volume. And then so B is going to be the critical specific volume over 3. So that gives me the parameter B. So now that we have our parameter B, we're going to take our parameter B and plug it back into this equation up here to solve for our parameter A. So we're going to have the gas constant R times the critical temperature over the quantity of the critical specific volume minus B, which in this case is the critical specific volume over 3 squared, equals 2 times A over the critical specific volume cubed. We are going to have the gas constant R times the critical temperature over 2/3 the critical specific volume squared equals to 2A times the critical specific volume cubed. And so then distributing the square, we're going to have 9/4 times the gas constant R times the critical temperature over the critical specific volume squared equals to 2A over the critical specific volume cubed. And then we're going to move this over to the other side. So we're going to have 9/4 times the gas constant R times the critical temperature over the critical specific volume squared times the critical specific volume cubed. And so these will cancel, leaving us with 9/4 times the gas constant R times the critical temperature times the critical specific /volume equal to 2A. So dividing both sides by 2, we are left with the parameter A equals 9/8 times the gas constant R times the critical temperature times the critical specific volume. So we now have our parameter A. So we have found parameter A and parameter B. Alright, so now that we have used van der Waals equation and the critical point on a PV diagram to derive the parameters A and B that are in van der Waals equation, what we are going to look at next is the compressibility factor. Now, the compressibility factor what we're going to call Z, is the ratio of an actual volume to the volume predicted. So earlier we mentioned the ideal gas law, which is PV, pressure times volume, times the gas constant R times temperature. Again, we're assuming volume is volume per mole, so the specific volume is volume per mole. So we can omit the N that is normally seen in the ideal gas law because it's just 1. And so